Hello everyone. In this video we are going to talk about weld design and weld symbols, which is a very important topic in machine design. So as always, the pictures and equations are taken from Shickley's Mechanical Engineering Design book. And before I go and talk about the stress calculation in weld, I want to show you the weld symbol. I talked about this in one of my technical drawing videos and drawing in CATIA. But here I want to remind you that the symbol for welding, if you see it anywhere, is like this. It's in basically leader arrow, and it can have this tail at the end, and there are some writings above and below it, either both of them or one of them. And at this corner here, you can have these circles. So this is the overall appearance for a weld symbol. So in a drafting, you might see something like that. If you see that, that is a weld symbol. But what does it mean? What goes on this weld symbol? So there are a bunch of information that can go in, like what? So the biggest part of the information are typically on this top and bottom. What are they? So if the information is shown on the top of the symbol, above the symbol here, that means the other side. If it's below the line, it means this side. So what does that mean in the first place? So take a look here. I have a weld bit for this T section. I have a weld bit. When I'm referring to, I have a weld bit both on this side and the other side of the member. That's why I show the shape of the weld bit here. I show it both above and below. But if instead of that I used this symbol here, I used this, and I did this guy here only on the top part, and I said 5. What does it mean? Since it's above it, it means only this side, the other side should be welded, not this side. Okay? You see that? So if instead of this one, I use this, then only this other side should have been welded. On the other hand, if I got rid of that and if I brought it down here, since it's below, that means this side. In that case, only this side should be welded and the other side should not. If I have it on both, above and below, as you can see, then it means both sides. Okay, so that's the first thing you need to learn. Now, if I wanted all around a circular junction, a circular connection, right? If it's all around, then I put the circle at the corner point. That means this weld has to be all around, as you can see over here. Okay, so that symbol, as you can see, that circle means what? All around. If it has to be done in the field, then I can put this basically filled circle right here. What information now would you put above and below? So the information is, as you can see here, it's what? It's the contour symbol, so what kind of shape of weld it is, as well as what? As well as the size of the weld. Okay, those information are the major things that go here. The size and the contour symbol typically are the most important one. So you can see here, this is the contour symbol. And here, this number 5 is the size. So what does that mean? Let's talk about it. So there are different shapes of weld bead that you can have. You can have the bead shape, which is a semicircle. You can have a kind of triangle shape that is called a fillet weld. And you can have a plug or a slot weld, which is kind of like this trapezoid. And the groove that you create between the two objects to be welded together, because sometimes you need to create a groove. Like in this case, you don't need a groove because one part sits perpendicular to the other one, so no groove is needed. But if you put like a head-to-head, or you might call it butt welded scenario, here you want to weld this piece to this piece, then between these two there should be a groove that you fill it with the welding material. And this basically groove that you have here, in this case it's a rectangular groove. In this case you cut it like a V, so that's a V groove. In this case it's a double V, so you see the groove is like this on both sides, above and below, and in this case that's like a half V basically. Okay, so these are different symbols for the grooves between the members. So if it's a half V, we call it a bevel. If it's a V, we just call it a V. If it's just a rectangular, we call it a square. And then you have U and you have J grooves. So there are different types of grooves, different types of the fillet bead shapes and symbols. So those symbols can be shown above and below the line. And if a number is behind them, is to the left of them, as you can see, if you see a number to the left of the symbol like that, or here, that is the size of the weld bead. What does that mean? It means if it's a triangle like this, in this case, this guy from here to here, or this one, is 5 mils. Okay, so that shows you the size of the weld bead. That is the size that you can see here. Okay, there might be a finish symbol which you can show it above it. Okay, in this case I don't think I have an example for finish symbol, but you can have a finish symbol for above the weld bead and say what kind of finish you want, and then if that groove that you have, you need to specify the size of that groove, then you can put it here. For instance, if you look at this example, you say this double V groove should be at angle 60 degrees. This V groove is 60 at above, and the root opening, the bottom of it, should be 2 millimeters. Here you have not specified any value for this square groove. Here for this kind of bevel groove, you say the angle should be 45 degrees. So specifications for the groove will be right next to the shape of the groove, and the size of it will be behind it. Okay? Then, if your weld is not a continuous weld, it has a bunch of patches like this scenario, so you have one patch here, one patch here, one patch here, it's not a continuous one, then you need to specify basically the size of each patch as well as the offset between the two, which you might call it pitch. Okay, and that is what you do over here, length dash pitch. So here, when I say 60, that's the length of each patch, and the offset between them is what? 200. So that's another information that goes there. If you have a bunch of spot welds, the number of spots will go below here. So I don't think I have a spot weld here, but if you have a few spots, like maybe, I don't know, 6 spots here, then you can show that 6 down here. Okay, here I did a little bit clean up, and now there are other information as well here, like in this tail area. You might have specifications, other specifications specifically for processes and so on that you might use. And this field weld symbol, you see it's like this, but sometimes they use a flag like that. So if you see a flag like that at that corner, that also means what? The assembly is to be done in the location, in the site, in the shop. Okay, so you don't do the welding here, you do it where the part is to be used typically, and to be assembled, you do the welding in place. So that is called the field weld symbol. So these are most of the information about a weld symbol. And there are other shapes too, like for instance, If the plates are thick, you might want to do a butt welding. Then you might want to use a U or a J groove to allow more molten welding material to fill in and attach the parts. Or if it's a T section, right, it's a T plate for thick plates, right, a T joint, then instead of just having a simple fillet weld like that, you cut this part that was straight, you cut these two areas, and you basically with this profile show that you have grooves in the part. If the parts are to be welded at 90 degrees like this, and this is not going to be for heavy loads, then you might do a corner weld, and that you can do with a fillet right here. This is not the perfect triangle, but you can fill it in. And if it's sheet metal or light loads, you can also put the edges right next to each other, attach, and then fill it with this. Okay, so this is kind of like a square, but of course a little bit rounded. But you can do an edge weld. So you can do edge weld or corner weld, and if you have thick plates, you might do other types of welds and grooves as well. The world of welding is very, very large, and talking about weld is not something you want to do in one video here. So I just try to familiarize you with basic shape of a weld symbol and what info go on it. What I want to focus mostly in this lecture is stress calculation for weld. Okay, that is the main focus here. So let's talk about that. And when you weld two parts together, depending on how those two parts are connected and what kind of load is applied to the welded joint, there might be different formulas and different scenarios. So here we just look at some of them, not all possible scenarios. So this is not an exhaustive list. A simple scenario is where two parts are butt welded head to head, and here you see a V is used, a V groove is used, and the parts are under tension. So these two parts are being pulled apart, and the height of this throat, which you call it, the height of the weld, which you call it weld throat, that is H. The length of the throat is L. And here, in this case, the weld has a reinforcement. What is reinforcement? Reinforcement is this extra basically projection of the weld bit out of the part, okay? So here it's not completely sanded and made it flush. This extra portion on the top of the part is remaining for reinforcement. Okay, even this part you might call reinforcement too. So that we do not count toward H. H is only the thickness of this material and the thickness of the weld that we count. So the H does not include reinforcements, okay? And H and L, we call them the throat and the length of the weld. In this case, just like a similar stress calculation, this force is applied to what? Is applied to a rectangular cross section, which is this. And it is L times H. So if you divide F by H times L, that is your normal stress, okay? Now, sometimes the butt weld with a V joint, with a V groove, is under shear. So the forces are tangential like that. Still, that force divided by the same cross section, which you have here or here, that is going to be the shear stress. Okay, so very simple. These are very simple scenarios, but not always it's as simple. For instance, you might have a what? You might have a transverse fillet joint under tension. What is this? In this case, you have more than two parts. You have three parts, part one, part two, part three. And they are welded by these two fillet welds, okay? So we call it a transverse fillet joint, right? You see? And in this case, again, the system is under what? Under tension. So you have F and F, and you have 2F on this side for static equilibrium. In this case, there is no f on this side that you can simply say, hey, I divide this f by this cross section. Okay, so in this case, the stress calculation is a little bit more involved. In this scenario, if you cut inside the weld and get this area here, go to this plane where the throat of the weld is defined for that cross section. So in this case, distance CB or AB is not going to be the throat. Okay, the throat is this shorter distance from point B to the line AC. That is your throat, and which in this case is at 45 degrees. But here, for the sake of completeness of analysis, we find the shear force and the normal force on a plane that is at arbitrary angle theta with respect to the vertical line. So this is like a Mohr circle analysis. We cut the weld at arbitrary angle theta. We find the shear force and normal force, which clearly from here, from static equilibrium, Fs should be F sine theta and Fn should be what? F cosine theta, right? Because you have this force, you have this force, and you have this force at equilibrium, right? And this angle is theta. So if you decompose this F onto the plane of N and S, right, this angle is theta. And so this F, the component of that over N is going to be a cosine, and the component of that over S is going to be cosine of 90 minus theta, which is going to be sine of theta. So these are the shear and the normal force on arbitrary plane. Now the cross section is going to be T times L, where L is the length of this material, right? So if these plates are at length L, now the thickness that you use, as we said, is not going to be this H anymore. It's going to be T. What is T? T is this red line that I showed you. That is T. But here, this T is for arbitrary angle theta, not necessarily 45-degree angle. So at this cut plane here, this x-axis, along this, we have to calculate this distance T. And for that, we can use geometry. Once we found this T multiplied by L, we get the cross-section that we need. So we divide these forces by that cross-section to get the stress components, sigma and tau, right? So this guy, if you divide it by A, that's going to give you sigma. If you divide that Fs by A, that is going to give you tau. So the question is, what is this T as a function of theta? Because that does depend on theta, and that does depend on H. So for that, we can use trigonometry, okay? And here, law of sine is used. As you can see, it says T over sine 45 is H over sine 90 minus theta plus 45. Where does that come from? For that, we need to focus on this triangle. We need to focus on this triangle. So I redraw it for you over here with a bigger scale. Like this. And let's see what angles we have. This angle here is clearly theta, right? What is this angle here? This one. Well, remember, that's this angle here. And this angle is clearly what? 45 degrees. Right? So if that is 45, then this guy is also 45. So this guy is clearly what? 45. And the total angle in a triangle is what? 180. So this guy is going to be 180 minus 45 minus theta. Right? And 180 minus 45 is 135 minus theta. So this angle is 135 minus what? Theta, which you can see over here. Now, this member here is T, and this member here is H. So I use the law of sine. I say T over sine of angle in front of it, which is 45, is the same as h over sine of angle in front of it, which is 135 minus theta. So I set these to equal, and from here I can easily get what? I can easily calculate my t. Why? Because sine of 135 minus theta, as you know, is going to be what? It's going to be sine of 135 times cosine of theta minus cosine of 135 times sine of theta. And as you know, sine of 135 is a square root 2 over 2, and cosine of 135 is negative square root 2 over 2. So if you simplify it, it's going to be square root 2 over 2. Those two would cancel each other. It's going to be sine theta plus cosine theta. Right? That's this guy. And this sine of 45 also is square root 2 over 2. So if you cancel these square root 2 over 2's with each other, right? So you have one here. Sorry. You have one here and you have one here. Simplify, you get this formula for t. Now you plug it into A and divide those forces by A. If you do so, your shear stress is going to be F over HL times this, and your normal stress is going to be this. So now you found your shear stress and normal stress on a rotated plane. Now you go to the Mohr circle, and you can look at maximum stress, or if you want to use 1 Mises stress, you go to 1 Mises stress and find sigma prime for angle arbitrary theta. Remember, in my previous lecture, I showed you that sigma prime for von Mises, when you only have 1 sigma and 1 tau, is the square root of sigma squared plus 3 tau squared. So you plug them in, simplify these two into this, and guess what? You can get a equivalent stress for your 1 Mises sigma prime. Now, at what angle this sigma prime is going to be maximum? For that, you need to take derivative of this sigma prime. You need to take derivative of this function with respect to theta and set it equal to 0. If you do so, you'll find that at angle 62.5 degrees, the maximum of sigma prime is going to be 2.16 F over HL. This is going to be your maximum what? Maximum distortion stress, sigma prime. And if it's a static loading, this guy has to be less than or equal what? And if you don't want any yielding, it has to be less than or equal SY divided by what? By the safety factor. So there is no permanent deformation in the weld that you have. Okay? Just like that. So in this case, the calculation is a little bit more involved. In this previous cases, no. Because in this top case here, it's a simple thing. And again, here your, let me clean it up. Your sigma should just be less than SY over safety factor for this scenario here. And in this case, this should be less than or equal tau allowed divided by safety factor. Or tau allowed, just tau allowed, and tau allowed is typically the shear stress divided by 2 and then divided by the safety factor. Okay, so in these two scenarios it was easy, but in this case, as you can see, the computation is a little bit more involved. And another scenario that might happen, again, this is not an exhaustive list, but another scenario that can happen is parallel fillet joint under tension. So in this case, as you can see, right, it's quite a bit similar to this scenario with some differences, right? So if you look at the shape of this one, and if you look at the shape of that, you see some major differences, right? but some similarities at the same time. So if I just bring that guy, because it might be a little bit confusing, if I just draw that thing down here. So here you had your one member on the top, one member in the middle, and one member at the bottom, and you were pulling like this. Okay? I added some edges to make it a little bit more 3D for you, so you can see it better. And you see it's just the geometry really, right? So in this case, the weld bit is here. This is the weld bit, right? And the force is like perpendicular to the weld bead, while in here the force is parallel to the weld bead. And in this case, if you want the cross section, for the shear stress, it is going to be at angle 45 degrees, right, times h. So that h, this distance here, that is going to be 0.707 times h, and that multiplied by L is going to give you the cross section. F divided by that is the shear stress. This guy has to be less than or equal what? T allowed. Let's look at one more scenario. I just wanted to stop it here, but let me show you one more scenario, and that is if the weld is under torsion. How would you go about it? So here you have a beam in purple, and the two welds on the top and the bottom are with length L in yellow are shown, and there is this force F, and this force F is going to create two shear stresses on the welds. One is a primary shear tau prime, and the other one is a secondary shear tau double prime, and the total tau is the resultant of the two that you need to compare against the allowable tau. So what are tau prime and tau double prime? Tau prime is direct shear, so you have to divide that shear force at that location, which is V, and that is as a result of F, and divided by the cross section A, and A here is not the cross section of one of these welds, is the total area of all of the welds. So you have to calculate the throat area of all of the welds, and by throat, remember here we are talking about what? We are talking about this basically narrowest or the smallest thickness in the cross section. You have to go for the smallest cross section possible and multiply that by the length of what? By the length of L. And you can see that here too in this initial one, right? In this kind of trapezoid, the smallest cross section you can get is H here, the smallest thickness. So if we calculate that H, whatever it is, multiply by L, that is this A, and if you divide the V by A, that is going to be tau prime. And V here is, if you cut this beam at any point, there is a shear force V and there is a bending moment M, and you have done that in solid mechanics. So V in this case could be just F or depend on F because there might be other forces. But V at that point is the shear force. You divide that by A, that gives you the primary shear tau prime. The second one is coming from torsion directly, and that is TR over J. In this case, T is the same as M, so you can call this T if you want. TR over J. T is the torque of the, at that point, or the torsion, so that is the same as this M, again, if you want to call it. And that comes from your bending moments. In this case, it is going to create a torsion because these are in the same plane with this, right? These two are in the same plane with the beam, so it creates torsion on those. R is, for any point, R is the radial distance from the centroid of the weld. So this is the centroid, this point O is the centroid of the weld group. So the centroid of that top yellow part, and the bottom yellow part is this point here. The radial distance of any point to that is R, and J is the total polar moment of inertia of, again, both of these weld groups, again, with respect to what? With respect to the centroid, as well as this M. M is also calculated with respect to that centroid as well, or T you might call it. Okay, and then once you have T prime and T double prime, we see at which point these two will make the highest resultant. Because for instance, if you go about this point, in this point tau prime is still downward like that, by tau double prime, right? Tau double prime is going to be upward. Okay, so you got that, and tau double prime is going to be perpendicular to this line, so it's going to be like this. And in this case, the summation, if you look at it, is going to be this, the resultant, which might be smaller than this one. Okay, so the closer the angle between, the smaller the angle between tau prime and tau double prime at any point, that is the point with maximum resultant vector tau that you need to compare against tau allowed. Now, as an example, let's look at this scenario here. So let's say instead of the simple scenario where these two are simply just parallel to each other and calculating A and J is easy in this case, right? Let's look at a more complex shape that the welds are like this. They are at 90-degree angle with respect. So the beam is like this, for instance, right? And this force is applied here, and you welded it at the top and on the left. So in this case, if we go with the dimensions we have, these D2 and B2, D1 and B1, if you multiply together and add together, that is the total area that you have. Okay, assuming that these are the smallest thickness, otherwise you have to multiply them by a fraction of it, like 0.707 or something. And for the J, here you have two groups, group 1, this vertical one, and group 2, the horizontal one. You have to find the polar moment for each one of them. And what you do here is you calculate each one of them with respect to their own centroids, G1 and G2. So for this guy, if you want to calculate J about centroid G1, we have to find I of XX and I of YY, then add them together. And from statics, you know, they are B1 D1 cubed over 12 and D1 B1 cubed over 12. You add them together, that's J of G1. Similarly for G2, you just use B2 and D2. Okay, and then these are the J's with respect to their own centroid. But we want to remember the total J that we said has to be with respect to the centroid of all of them, centroid of the groups. So it has to be with respect to this point. Therefore, we have to use what? We have to use parallel axis theorem. And you see this J of G1 is added to it, A1 times R1 squared, where R1 is this distance. And the second one is added to R2 squared times A2. So you see here parallel axis theorem is used. And the way to find R1 and R2 is by what? By finding the location of the centroid, which is shown by X bar and Y bar. And that you can easily get from static formulas for centroid. So you multiply each one of the A's by their own X's, and X1 and 2 are X1 of X of G1 and X of G2, Y of G1 and Y of G2. So this X1 is not X of what? This is X of, as you can see, that is X of what? That is X of centroid 1, this is X of centroid 2. And Y1 and Y2 are Y of centroid 1 and Y of centroid 2, as you can see over here. Okay, yeah? So with those, you calculate X bar and Y bar, and then you find the distance of the point X bar, Y bar to the point X1, Y1, or X2 and Y2, and you get what? You get these distances, right? R1 and R2, and you can plug them and find the total J, and you have total A. And of course, again, you have to see which point has the largest max value for this R times J and M. So you have to look at R corners here. Typically, the largest stresses happen at these corners. So you come to this corner, you come to this corner, you come to this corner, and this corner. And see which one you calculate the tau prime at all of these 4 points. The T prime is the same for all of them. It's all downward in all of them. The tau double prime is not. It's perpendicular to the radial location. So for instance, in this case, if I do a little bit cleaning, if I want to know tau double prime here at this point, I have to connect it radially to G, and then in this case, it's going to be perpendicular to that. Okay, or if I want this corner, I connect it again this way, draw it with a line. See if I can do a better line, and then this is going to be perpendicular to that again. Okay, so that is what? That is your tau double prime. Your tau prime in all cases, in this case, could be downward. And then you have to see which one of these will give you the maximum resultant tau and use that for the design. Okay, so this is under torsion. And you can have other scenarios too. You can have bending, and the formulas that we had in solid mechanics, we're going to use them, but pay attention that it might be a combined loading. So if you have a combined loading, what would you do? You find the primary shear stress due to external forces. If there is a secondary shear stress due to torsion or bending, you also calculate that. And then you combine these primary and secondary shears, you get your total shear, and use that. Then you also need to know the strength of the parent metal, the strength of the weld metal, and then calculate how much load you can have based on the given safety factor for the parent metal and for the weld metal. So in welding, it's not just enough to focus on the welded material. You need to also look at the parent material too and make sure both of them are safe. Okay. Now, speaking of strength of the welding material, because strength of parent material, parent metal, you just get it from the ASTM or any other table for like whatever steel it is or whatever metal it is. But what about the welding material? What is the strength for welding material? Here I copied some tables from my book. I scanned and copied here for you the tables for welding material or electrodes here. So it's assuming that it's arc welding, or yeah, I think these are arc, and yeah, they are for arc welding. And here you see for different categories like E60, E70 something, E80 something, right? These numbers are to determine the strength, and the rest of these parameters are for the rest of the properties of electrode, like the current that you need and so on. So you see that if you have an E60 something electrode, these last two could be any digit, right? That is specifying the other properties of electrode. Then the tensile strength, right, in kpsi is 62, or megapascal is 427, and the yield strength, right? So this is like the ultimate strength. The yield one is 345, okay? And it shows also how much elongation they can have at the failing point. So you see, these are properties. One other thing I have to mention is most of the time these electrodes are stronger than the parent material. So most of the time your parent material metal can break, but the welding material is not going to break, okay? So keep that in mind specifically for static loading. Now, what kind of safety factors you have to use? Because remember, we said that these numbers have to be less than what? They have to be less than some yield strength divided by a safety factor. So the yield strength, let's say for welding, we got it from these electrode properties. What about safety factors? Here you see, based on the American Institute for Steel Construction, AISC, they have some suggestions for safety factors for different types of loading. So they said, for instance, if the welded area is under tension and it's a butt welding, use 1.67. If it's like a bending butt welding, then use between 1.52 and 1.67, right? If it's a simple compression, then use this number for permissible stress. right? Which is basically again 1.67, right? If it's under shear butt or filled weld, then use 0.3 SU. Okay, instead of SY, use SU. So they show you some permissible stress or correspondingly some safety factor. Now, if it's fatigue, if the welding area, the welded area is under fatigue, under cyclic loading, then you have to use different safety factors. And the way you use safety factor is you can use KF. Remember, KF was the miscellaneous. And one of the factors of that miscellaneous, if you remember, it was a stress concentration, which I mentioned. So the stress concentration, which is going to affect your KF, and the bigger it is, the smaller endurance limit you're going to have. You see that if it's a reinforced butt weld, use a 1.2 for KF. If it's end of parallel fillet weld, use 2.7. If it's a T-bite joint with sharp corners, use 2, and so on. Okay, so you see you have typically a little bit higher numbers here. And because in fatigue, the strength of the weld goes down relatively highly, relatively significantly. And typically when you have cyclic loading, the best way to have a permanent connection is through bolt and nut, not through weld. And that's why you see that in order to make a building stronger against earthquake, they typically connect the beams by bolts and nuts. In recent constructions, if you look at buildings, they connect the beams by bolts and nuts instead of using a lot of welding, because weld fails a lot easier against fatigue than bolt and nuts. Okay, so I don't want to get into the topic of that, but just keep in mind that fatigue affects welding quite a bit significantly. So these are some information about how to go about calculating stress under different types of loading and how to get the strength. And there are other tables similar to this for other types of welding. So if you're not doing arc welding, you're doing gas welding or anything, TIG, MIG, whatever it is, there are similar tables for the strength of the welded material. And there are suggested similar safety factors or stress modification factors for fatigue. And remember one more time that not only you have to check the weld metal, you also need to check the parent metal. Make sure they are both safe, not just one of them. Okay, that is very, very important. So hopefully the video was useful to you, and I'll see you in the next lecture. Thank you.